The last speaker for today's evening session is Andrew Brooke-Taylor from the University of Leeds, and he will talk about measurable cardinals and limits in the category of sets. Yoroshiku onegai shimasu.
Thank you very much. Thanks for having me here. It's great to be celebrating Sakai's reduction in administrative tasks. So Joanne recommended that you keep playing the piano or do it more now that you're retired. I'd recommend doing some more skiing now that you're retired. We had some good times skiing together while I was a postdoc in Japan. I also seem to bump into Sakai quite a lot in Catalonia. What I wanted to talk about today is actually something that came out of, it's already been mentioned this morning, this 2018 meeting we had for Joan's birthday in Catalonia, which Sakai was also at. Also Rositsky was there and I got talking to him. So this is work that came out of that. But let's start at the very beginning. So probably most of you are comfortable with categories by now. Enough people talk about them. But a category has a class of objects. They've got morphisms between them and a good notion of composition of morphisms and of identity elements. And so kind of some good examples to bear in mind is the category of all sets with the functions between them, and the category of groups with group homomorphisms as the morphisms. Okay, and so my title mentioned limits. So in category theory, there are different ways to present it, but we talk about limits and co-limits of diagrams. So for the purposes of this talk, I want to just think of a diagram as just a set of objects and some morphisms between them. And then the limit of a diagram, the reason I've connected with my iPad is that means I can draw some pictures as I go. So the limit of a diagram, we've got some diagram, call it D. So we've got some objects, A, B, C. We've got some morphisms between them. A limit is an object along with a cone of so-called projection maps. The point is they're maps to all of the objects in the diagram such that the triangles all commute. So that's what it means to be a cone. And a limit is a universal such thing. So anytime you have any other object which gives you such a cone, I won't bother drawing in the Z to C map, but anytime you've got something like that, there is a unique map from this other Z to the limit that makes all the diagrams, all the triangles commute, okay? And then let's change color. A co-limit is just the same thing in reverse. I guess I've already used the letter C, but let's call it col. The co-limit, you've got a co-cone of morphisms to this co-limit object, and then anytime you have a similar such co-cone, there is a unique map between them. Okay, so good abstract definition. What does it actually mean in practice? So in the category of sets, every diagram has a limit and co-limit. So if you have a diagram of sets with functions between them, if you figure it out, the limit it's a subset of the product of all the sets in your diagram. And in particular, it's the subset consisting of, well, the product is sort of tuples, one element chosen from each of the sets in the diagram. And so the limit is the set of those tuples where all the coordinates cohere under the functions of the diagram, okay? In the category of sets, you also have all colimits. So if you've got a diagram of sets with morphisms, functions between them, the colimit is just the disjoint union, and then you identify elements with their images under these diagram functions. Okay, so set is a very nice category. It has all limits and colimits. The category of groups has all limits and colimits too. Okay, so limits, if your diagram in the category of sets happen to be all groups and group homomorphisms, then the limit that I've described, this product with taking the tuples where the elements cohere, that is also a group. So that's the limit in the category of groups. And colimits in the category of groups is just the free product modulo, again, identifications, things that need to be identified. Okay, so we can have fairly arbitrary limits and colimits of diagrams. And an important special case is if you've got some set of objects A in a category, and you've got some object C of the category. Let me start drawing pictures again. I like purple for some reason. So we've got some set A of objects. We've got some object C in the category. The canonical diagram of C with respect to A is the diagram where for every object in A and every morphism, let's call it F from A to C, we have this copy of A, okay? And I'm going to just use a subscript F to note that this copy of A came from F. So we could have multiple copies of A. Let's say AI, if we've got a different morphism I from A to C, okay? So our diagram is going to have a copy of A for every morphism from A to C, and that's for every different element of curly A. And then the morphisms in the diagram are going to be the functions or the morphisms H, so that's BG. It's going to be the morphisms H that make the triangles commute. Okay? So we've done all of this thinking about this cone of all possible maps to C. Okay? And then we're going to, there's probably a slicker way to change the color rather than bombing out of editing and coming back, but it works. So let's stick with that. Once we've got this whole complicated diagram of all maps to C, then I'm going to forget about C and the maps to it and look at this thing in and of itself as a diagram. Okay? Now, the nice thing about it is if I unforget C, if I look at C and all the maps to it again, that's a nice co-cone from this diagram D to C, okay? So then you can ask, well, is that co-cone, does that make C a colimit of this diagram? Sometimes it will be and sometimes it won't. Okay, so if this kind of canonical co-cone from the diagram to C actually makes C the colimit of the diagram, then we say C is a canonical colimit of objects from A. Okay. So also, if every object in your category is a canonical colimit of objects from curly A, then we say that this set of objects A is dense. So some examples, in the category of sets, omega, the set of all finite ordinals, that is a dense set. So why is that? Well, every set is just the colimit of the diagram of all of its finite subsets. Okay? And the finite subsets you can think of as the images of functions from finite sets. Similarly, any set of representatives of all the isomorphism classes of the finitely generated groups is going to be dense in the category of groups, because every group is the colimit of the diagram of all of its finitely generated subgroups. Okay, so these are nice categories with nice, dense sets of objects that give us everything as a colimit in a nice canonical way. So being a canonical colimit of objects in A is stronger in general, or at least it certainly seems so, and I'll come back to this, stronger in general than just being a colimit of some diagram of objects from A. Okay. Well, I guess the way I've phrased it, I'm going to answer this on this slide. Here's an example. Consider the category of all real vector spaces with linear transformations, isomorphisms, as you might expect. Okay, I'll do some drawing again. Let's switch back to the more visible purple. So let's just consider A only containing one object, the reals. Okay, well, certainly every object of the category of real vector spaces is a colimit of objects from A. It's just choose a basis and choose the corresponding maps, and then your vector space will be the colimit, well, yeah, the colimit of that many copies. But this A is not dense, okay? It's a slightly weird thing, but if you consider R2, so I claim that R2 is not the canonical colimit of all maps from R to R2, okay? And the reason is this: if you consider another copy of R2 and you have a function phi that respects scalar multiplication but not addition, okay? So let's actually, that might speed it up. Anyway, take some phi that takes the unit disk maybe to some elongated oblong. So it's not a linear transformation, but for every one-dimensional subspace, it is linear. Okay, it's just stretching it out. So then you've got the you've got all the mappings from R to R2. You've got that canonical diagram, but it doesn't make R2 the colimit of that diagram, because if you compose that with phi, as far as this one-dimensional space R is concerned, all the maps from it to R2 given by first go to R2 and then hit it with phi, those are all still linear transformations. They're just one-dimensional stretching. They're different amounts of stretching in different directions, but that's fine. The co-cone doesn't catch that, okay? So this R2 with the canonical maps from R is not a co-limit object in that sense. Okay, it's not the co-limit of the diagram we had on the previous slide for all the maps. Okay, so this singleton of the reals is not a dense subset of R vector spaces. On the other hand, there is a dense subset of real vector spaces if you take even singleton R2. Okay, that's got enough interplay between two different dimensions. You can check that will make any subspace will be the canonical colimit of R2 maps. Okay, so I want to explore this distinction between ordinary or just arbitrary limits and canonical colimits. First, I want to mention, again, this is probably something most of you have seen before. If you're given a category, the opposite category is the category with the same objects and really the same morphisms. You just declare that they point in the opposite direction. Okay, so for example, we can consider the opposite category of sets. So the objects are sets, the functions between them are, functions between those sets are the morphisms, but a function from X to Y is considered as being a morphism from Y to X. Okay. Right. So very natural old question, is there a dense set in this category set op? Okay. So I want to dig into this. This is not our work. This is an old result of Isbell, but our work will build on top of it. So if you've got any cardinal kappa and any set X, if you consider the canonical diagram in set op of X with respect to the set of ordinals of size less than kappa, okay? So since the morphisms are reversed, so the canonical diagram was a colimity sort of thing. So with the morphisms reversed, this canonical diagram is a diagram with an object for every function from X to an ordinal in kappa, okay? And then you have functions H within that diagram if they compose in the right way. So that's good to draw the picture. So we've got cardinals less than kappa, alpha. We've got our set X. We've got all the functions from X to ordinals less than kappa. Okay, that's the canonical diagram in set op that we're talking about. So now a function from X to some alpha less than kappa, as usual, we can think of that as in terms of the partition of X that it defines. You identify F with this partition of X into the F inverse of gammas for all the gammas in alpha. Okay, and in that context, so let me draw in this H. If we've got an H that makes the diagram commute, in that context of partitions, what do these morphisms do? Well, they're just going to coarsen the partition. You think of F as pulling out the different pieces of a partition of X, and then H is going to squish some of them together, okay? so the functions in this diagram represent coarsening maps. So, okay, what's the limit of this? What's the co-limit in set op? So therefore the limit in set of this canonical diagram. Once we've, again, once we've, as before, just thrown away the maps from X and just look at the diagram that's left, what is the limit of that diagram in the category of sets? Okay, well, we had a complete description before of what limits in the category of sets are. They're elements of the product of those ordinals where, so right, the product over all the ordinals in the diagram. So in the alpha F coordinate, you're choosing an element mu F of alpha F. So from the partitions perspective, this corresponds to just choosing a piece from each of the partitions. And in such a way that the coarsening maps of the diagram respect which piece is chosen. Okay, so we can think of this as choosing a big piece from each partition. If you've chosen the big piece and then you coarsen and squish more things onto the big piece, well, the image of that big piece should still be the big piece. Okay, so from this point of view, the intuition, it does actually play out. These choices form a kappa complete ultrafilter on the set we started with, X. Okay. So in particular, by coarsening, if some subset Y of X is chosen in any partition, well, it's certainly chosen in the two element partition of Y and the complement of Y. And from that, we can see that actually Y must be chosen in every partition that contains it. Okay. So we can let our ultrafilter U be the set of those Y subset of X such that Y is chosen in some partition in which it appears as a piece. Some is equivalent to any in this case. So I mentioned the two element partition. A nice, a slick way to phrase that is, well, think of the characteristic function of Y. So it's a map from X to 2, takes the value 1 on members of Y and 0 on other things. So then the ultrafilter is exactly those Y that are subsets of X such that the element in the tuple in the limit that is chosen corresponding to the characteristic function for Y, the piece that is chosen is the one piece. It's the piece corresponding to Y. Okay, and then you can check. My iPad is struggling to keep up. I hope it will catch up, but you can check that this is indeed a kappa complete ultrafilter. So I've just there got the upward closure, the kappa completeness, and then the ultraness. And it's just a case of finding the right coarsening maps in the diagram. Okay, so I won't go all the way back to the picture, but we started with this canonical cone from X to the diagram. We've figured out that the limit cone, the limit corresponds to all the kappa complete ultrafilters. And then, so, well, since that's a limit, there must be a map from X to the limit so that the canonical cone factors through. Actually, let me indeed go back to the picture I drew. There we go. So we've now, let's choose a different color, say green. We've now got the limit, which corresponds to, it turns out, all the ultrafilters on X. But we've got a cone from X to the diagram. By the definition of what it is to be a limit, there is this map from X to the limit. And all right, let me scroll back forward to where we were. Okay, if you figure out what that limit map is, it turns out it's the map that takes any element X to the tuple where the component for a given partition for alpha f, the component is just f of x. And if you flesh it out, that tells you that the corresponding ultrafilter is in fact the principal ultrafilter defined by that element of x. So a way to phrase this is you've got this map from X to the limit of the canonical diagram. That map takes members of X to kappa complete ultrafilters. It's the obvious thing of take the principal ultrafilter. So a cute way to phrase this is there's a non-principal kappa complete ultrafilter on X if and only if this map is not a bijection. Okay. In other words, it's not an isomorphism in the category of sets. Now, limits are only ever defined up to isomorphism. So another way to phrase that is it's if and only if X itself is not the limit of the diagram. Okay. So now, to phrase this in terms of the dense sets that I was talking about earlier, by definition, there is a dense set in set op if and only if for some kappa, every X is itself the limit of the canonical diagram. So we've just seen that's if and only if there are no non-principal kappa complete ultrafilters on any set. Okay. So this shows this old result of Isbell from 1960. There's a dense set in the opposite category of sets if and only if there are only boundedly many measurable cardinals. So this is a lovely formulation of measurable cardinals from a category theory perspective. It's very useful for things like getting lower bounds on things like Wheat-Vopienka's principle before Trevor Wilson came along, things like that. So natural question here, how important is it that we're using canonical colimits? Okay. So let's call a set of objects A from a category colimit dense if for every object of that category, it's the colimit of some diagram of objects from your set A. Okay. Maybe it's not the best terminology, but it's what we have now. So notice that colimit dense is actually weaker than dense. Okay. Think of colimit dense as being short for arbitrary colimit dense, whereas dense means canonical colimit dense. So in the case of vector spaces, we saw that the singleton of the reals as a real vector space is colimit dense. Anything is a colimit of the one-dimensional space, but it's not dense. But on the other hand, as I mentioned, R2 on its own is actually a dense subset of real vector spaces. So here's a question. Does every category with a colimit dense set have a dense set? If we've got a set of objects that generates everything by colimits, can you get a set of objects that actually generates everything by canonical colimits? And so the answer is no, okay? And this is a ZFC alone result. There are even examples of categories that are co-complete, so they have colimits for all set size diagrams, where you have a colimit dense set, but you don't have a dense set. So I want to go through the key part of the proof of this here. But I really like this result because the way we prove it is by a case distinction on whether or not there is a proper class of measurable cardinals. This is a ZFC result, but if there's a proper class of measurable cardinals, we prove it one way. If there's not, we prove it a different way with a completely different counterexample. So first case, I don't want to go into too much detail, but if there is not a proper class of measurable cardinals, if there are only boundedly many, this case was actually done in the late 80s by Adamic, Herlich, and Reiterman. So since there's only boundedly many measurable cardinals, in particular, you get Vopienka's principle failing. So you can get from that a proper class of directed graphs with no homomorphisms between them, just the identity maps. And then you've got this slightly funky little category of structures, X, Y, E, where X is a set, Y is a subset, so a distinguished unary predicate, and E gives you a graph structure on this subset Y. And then for the morphisms, you want functions such that the restriction to this subset Y, this graph, is actually a graph homomorphism. And then on the rest, you have a slightly more involved statement of where the elements can map to. They either map again to the complement of the graph or to something in the image of some homomorphism from this bad class of graphs that the failure of Vopienka's principle gives you. And then it turns out, if you flesh it all out, that with that particular category, if you take this 3-element subcategory, it turns out that is colimit dense. So every object in your category is a colimit of those 3 objects. But on the other hand, a short argument will tell you that a dense set would give you a homomorphism between these members of the bad class, curly G. Okay, I realize that's way too vague to really properly take in, but it's an oldish known result, okay? Younger than me, so it's not that old, but but it's a known result. So more interesting here, case 2, there's a proper class of measurable cardinals. So we want to come up with an example of a category that has no dense set, but it does have a colimit dense set. Well, the reason I went into all that detail with Isbell's theorem, that gives us, in this case, exactly what we want for the category. The opposite category of sets, if there is a proper class of measurable cardinal, the opposite category of sets does not admit a dense set, because no dense set will be big enough to capture all non-principal ultrafilters. So in that case, it suffices for us to find a colimit dense set of objects, okay? We want a set of objects in a set of objects that generates every set by limits, since we're working in set op. And actually, the key thing to observe is actually just take the set, the ordinal 3 on its own. 3 is co-limit dense in the opposite categories of sets. Okay, so I want to go through the proof of this because it's just a very hands-on combinatorial playing with sets kind of construction. It could have been done many decades ago, but anyway. So let's boil this down. I'm claiming that every object in set op is the co-limit of a diagram in set op just involving 3 element sets. So in other words, every set is the limit of a diagram just involving 3 element sets. Okay, so let's do it. First of all, if you've got a 0, 1, or 2, or even 3 element set that you want as a limit, you can do this with this diagram. You have the object 3, that's a 3 element set. You take the identity map to itself, and you also take another map. It doesn't really matter the specifics of what it is. The point is, it agrees with the identity map for as much of the set as you want to save, and then it disagrees otherwise. Okay. So then, in order, if you're looking at, let's draw. So if you've got this copy of 3, 0, 1, 2, you've got this other copy 0, 1, 2. Let's say we want the 2 element set here. I'm looking at two morphisms. I've got the identity map, the identity function, and I've got this other function, which is the identity on 0, 1, and then does something else to 2. Okay. What does the limit of that diagram look like? So let's use black actually. The limit of that is all the tuples. It's the subset of the product of these two. So it's the subset of the pairs. So for example, 0, 0, which what they project to should agree with both the blue and the green maps, okay? So the fact that it agrees with the identity function means they must be repeated pairs. So 0, 0 and 1, 1 are just fine, okay? But you can't have 2, 2 because if you want the triangle to commute, it should be 2, 0 for the green map. Okay, so if you kind of figure out what it means to make these diagrams commute, it tells you that these are the only members of the limit. Okay, so we can get 0, 1, 2, or if you like, even 3 element sets as limits of 3 element sets. So that's a good starting point. So now for arbitrary sets of cardinality at least 2, okay, instead of the partition perspective of things, think of pulling back the other direction. So you're stripping off individual elements from the rest. You've got some kind of artichoke, and you're pulling off pieces and kind of getting a collection of artichoke leaves that way. Okay, that's the intuition here. Actually, let me draw a picture for a slightly better intuition before giving the formal definition. So if we've got just a one element set, some big chunk, and we peel off T and some X, and then we can peel off even more T and some X and some X prime. Okay. And so X prime kind of maps down to T. We've peeled X prime. If you're working backwards through this diagram, you've peeled X prime off of T. T is like a central chunk. And then we've got the whole of X, and then we've got, so X, we've got X prime, X will map to X, X prime will map to X prime, and then everything else will map to T. Okay, so we fix some sort of chunk T to be like the core, and then we do every possible combination of peeling off one or two other elements. That's the kind of intuition for the construction, and because we can deal with one and two element sets, well, in fact, we only need to deal with two element sets, so we can do it this way. So we suppose we've got some set X, cardinality at least 2. So I'm actually going to choose this T to be a member of X. Ooh. Cancel. I don't want to. Okay, I'm going to have my T, which I kind of think of as the central core. One of the elements of X is going to actually be that T, okay? So I've got my T in X, and for keeping track of things, it's convenient. Let's take some little s that's not in X. So little s is like a garbage thing, but it's there to have a garbage option. Okay, so then for every member of capital X other than this T, let's consider the 3 element set of T, little x, and the garbage S. Okay, so on our picture, that corresponds to this two element set T and X here, but I'm also going to throw in this garbage S. Okay, that makes it a 3 element set. I said I was getting every set X as a limit of 3 element sets only, so this makes that work. Okay, so that's kind of, think of the KX as representing the 2 element sets, and then one step further back the chain, for any, we're going to take if you look at the sort of bottom paragraph of this slide, we're going to take all the 3 element subsets of X containing T. So that's the T, X, and X prime, like I've got on the row above. Okay, and then for any set Y containing little x, I've got this function f y little x being from Y to this kind of stand-in for the 2 element set, which just takes you to little x if that's what you are, and otherwise just gloms everything down to T. Okay, so our diagram is those KXs, it's all the 3 element sets containing T, with these morphisms F, Y, X for Y, a 3 element subset, and it's also all the functions fkxx from kx to kx. That's a little hard to unpack. That's just these maps. Let's change color. It's these maps from the 3-element set to itself that tell you S is garbage. Okay. Just like we had the construction of the 2-element set as a limit of 3-element sets, these maps on these bottom 3-element, these maps on the bottom 3-element sets kind of coded up as a 2-element set. Okay, so then I claim that the set you started with, X, is the limit in set, so the colimit in set op of this diagram, okay? With the limit maps, what you would expect, and having set up the notation this way, I can just define them as the fx little x, and similarly the maps as I drew them on this picture. Okay, so this so this map is, if you think about it, it's one of the F's, and this map, well, we call them G's, but those are the other diagram. The G's give you the kind of the limit cone down onto these 3-element sets. Okay, there are plenty of things to check here. You need to check that you do get X as the limit, that T is the unique thing that kind of stays with T all the way as you peel off everything else. But hopefully it's reasonably intuitive that doing every possible one of these 3-element sets with the peeling off the limit for that process, and so the limit of that diagram is actually the set you started with X. Okay, and I didn't need, although it was good for the motivation, I didn't need that 1-element set at all. Okay, so every set is a limit of 3-element sets, and that proves the theorem. So I know I've got 10 minutes left, but I think I'm done there. So thanks for having me. I wish I had a handy photo of Sakai doing some skiing, but I wasn't able to find one, I'm afraid. So thanks, everyone. So like Joanne, I'm happy to take any questions.
Hello?
Hi.
Yes.
Hi.
Hi. Who wants to ask? Who has questions?
I have a question.
Okay, please go ahead.
Do you have an example of a category with no colimit dense set?
In terms of a natural one, nothing is jumping to mind, but I mean, it's the sort of thing where I expect it to not be hard to construct one. And the question is then just how natural can it be? And so, yeah, the short answer is I don't know off the top of my head, but I imagine it's not too hard to construct one. I mean, you have plenty of categories which where you don't have colimits for all diagrams, so that's kind of a sort of counterpoint question, but certainly, yeah, there will be many cases. I think it's one of those cases where I can't give you an example, but I think most examples will be an answer to your question. So,
okay.
Yeah.
Okay. Other questions? Sakai.
You're muted again, Sakai.
Your mic is off.
Sorry, I don't know why I'm doing this repeatedly, but in any case, does your result or any other results in this context encourages the existence of, class many existence of measurable cardinals, or is it rather discouraging of the fact, or how do you see it?
It's a nice question. I guess, right, I guess you could phrase this result as saying the opposite category of sets is not that nice, is not as nice as it could be if there are a proper class of measurables.
Right.
But on the other hand, the boundedly many measurables case also showed that it's actually not that hard to come up. Well, I mean, I don't want to diminish the work of those three authors 30 years ago, but there are relatively natural examples, even if there are only boundedly many measurables for the same kind of pathology. So So you could view that as saying the pathology you get from having a proper class of measurables, if you even view it as pathology, it's not so bad. You get it in many other ways.
I see.
Yeah.
Do category theorists agree with this kind of worldview?
I probably not. To be honest, it's a good question. The question you originally asked, I hadn't really thought about it before. So I certainly haven't asked my category theorist collaborators about this. But yeah, certainly my impression working with Rositsky is that hands-on constructions with ultrafilters, they think are perfectly normal things to do. But elementary embeddings are some kind of magic. So the fact that we think they're equivalent is kind of complicates the picture of the stance they would take, I think. So I don't know.
Yeah, thank you.
Okay. Other questions? There is nobody now. No. Okay, I think there are no more questions. Then let's thank Andrew